Place a single charged particle in an electric field, and it accelerates along the field lines. But place a permanent electric dipole, two equal and opposite charges locked together, in that same uniform field, and it doesn't fly away. It twists violently in place, snapping into alignment while its center of mass remains perfectly still. To understand why, we have to look at the baseline environment, a uniform electric field. In this model, the electric force is identical in magnitude and direction at every single point in space. When we place our dipole at an angle, the field acts on both charges at once. The positive charge is pushed in the direction of the field, while the negative charge is pulled in the opposite direction. Because the charges are equal and the field is uniform, these two force vectors are identical in size, but opposite in direction. They cancel out perfectly. QE minus QE equals 0, meaning the center of the dipole experiences no net push or pull through space. While the translational force is 0, these opposing forces are physically separated by the length of the rod. They don't move the object forward, they create a turning effect. To understand the motion, we have to calculate rotation, not translation. We will derive the exact mathematical torque driving this alignment, and then test what happens to that motion when the field is no longer uniform. This requires a process called kinematic decoupling, treating the rotational mechanics of the system as an entirely separate event from its movement through space. This distinction explains one of the most common observations in physics, frictional electricity. When you run a plastic comb through dry hair, it gains the power to pull a neutral piece of paper right off a desk. But the paper has no net charge. If our model says the net force on a dipole should be 0, why does the paper physically accelerate toward the comb? Mastering the rules of the uniform field is the necessary baseline. Only by understanding perfect symmetry can we explain what happens when that symmetry breaks in the real world. We begin by isolating the dipole's geometry. We define the fixed, rigid distance between the positive and negative charges as 2a. Next, we define theta, the angle between the orientation of the dipole and the direction of the electric field lines. Because we have two equal anti-parallel forces acting at different turns, we have what is known as a couple. The torque of a couple is defined as the magnitude of a single force multiplied by the arm of the couple, the perpendicular distance between the two lines of action. Based on the parameters of Coulomb's law, the magnitude of the force acting on each charge is simply the charge, Q, times the electric field, E. To find the perpendicular distance, we use trigonometry. The distance between the two force lines is 2a sine theta. Multiplying these gives our initial equation. Torque equals QE times 2a sine theta. By definition, the electric dipole moment, P, is the product of the charge and the separation distance. Substituting P for Q times 2a simplifies our variables. The torque is now P e sine theta. In its final vector form, this is a cross product. Torque equals P cross E. This generates a rotational force acting normal to the plane, driving the dipole to align with the field. There is a physical limit to this motion. Once the dipole is perfectly aligned, the angle theta becomes 0. Since the sine of 0 is 0, the torque vanishes instantly. In a perfectly uniform field, a dipole's entire mechanical existence is rotation. It will spin until aligned, but it will never move through space. This brings us to a pivotal question. What happens if the field lines are no longer perfectly parallel? This is a non-uniform electric field. Notice that the field strength is no longer constant. It increases as the field lines converge toward the right. We'll place our dipole perfectly parallel to these field lines. In this position, the angle is 0, so there is no rotational torque. We are isolating the translational pull. The positive charge on the right sits in a denser, stronger region of the field. The force vector pushing it right is significantly magnified. The negative charge on the left is in a weaker, sparser region. The opposing force vector pulling it to the left is visibly smaller. The symmetry is broken. Because the positive force is stronger than the negative force, they no longer cancel out. This creates a net force that drags the entire dipole into the stronger field. If we flip the dipole 180 degrees, the negative charge moves into the stronger region. Now the net force reverses, pushing the dipole toward the weaker field. This is the core distinction. A non-uniform field unlocks translational motion, meaning a dipole will experience both an aligning torque and a directional pull. We can now resolve the mystery of the comb and the paper using these two mechanical rules. A negatively charged plastic comb generates a highly non-uniform field. The strength is intense at the teeth, but drops off rapidly as the field lines radiate outward. Neutral paper molecules have perfectly balanced charge centers, but the comb's field distorts the structure. It pushes negative electron clouds away and pulls positive centers forward, inducing a dipole. Instantly, torque twists their positive ends toward the comb. This polarization bridges the gap between macroscopic objects and molecular physics. The field essentially creates the dipoles it needs to interact with. Now we combine that alignment with the mechanics of the non-uniform field. Because the molecules rotated, positive charges are physically closer to the comb, sitting in a denser field than negative charges. This ensures the attractive force is always stronger than the repulsive force, resulting in a physical pull lifting the paper to the comb. The rule is consistent. Uniform fields yield torque only, while non-uniform fields yield both torque and net force. The cross products and trigonometric couples that we've calculated on this whiteboard actually define the hidden geometry of the real physical world. Mapping these invisible fields and their broken symmetries allows us to predict the exact path and force of energy moving through the world around us.